Today we are going to deal with few important algorithms with respect to binary trees, and these algorithms are known as algorithms. Hello, am I audible? Hello.
Yes, ma'am.
Okay, so let's begin with today's topic. So what we are going to discuss in this session is two kinds of traversal algorithms, recursive algorithms and non-recursive algorithms. So I think previously you have studied recursive algorithms and you may not probably have studied non-recursive algorithms. So in fact, non-recursive algorithms are really very interesting ones, and we are going to focus upon non-recursive algorithms, and we'll be having few exercises based on these kinds of algorithms. So with this agenda, let us start today. So let us revise the concepts. We know the binary tree. So binary tree is a finite collection of elements. It might be the empty collection also. A non-empty binary tree has a root element and the remaining elements are partitioned into two binary trees. A node in a binary tree can have no more than two subtrees. So any node in a binary tree may have at the max two subtrees, and those are called as left subtree and right subtree. In other words, we may say that the maximum out degree for a node in a binary tree is 2. Am I correct? Yes. So let's proceed. This is a pictorial view of a binary tree, a typical binary tree. So what we have is these blue are the nodes in our binary tree. So A is the root node. A is having two subtrees, left subtree and right subtree. So towards left of A we are having node B, and towards right of node A we are having node E. So this node B may once again have a left subtree and right subtree. Similarly, this node E may have the left subtree and right subtree. So this is how recursively, actually the definition of a tree is also recursive. So we are having a node wherein we are having left subtree as well as right subtree for the node. So at the max we may have two subtrees for each node, and recursively once again we may define that every node in left subtree and right subtree itself is a binary tree. So this is how recursively we may define a binary tree. So these are few of the examples of a binary tree. Please go through. So we may have empty tree as a binary tree. We may have a tree with a single node, or we may have such kinds of combinations of nodes. Simply we should understand that every node is having maximum out degree of 2. So only 2 children for a node are possible in binary tree. We know the basics of binary tree, so we are not going into the details of the basics about binary tree. This is just to recollect few important points. Now, as far as binary tree traversal algorithms are considered, let us understand first what we mean by a traversal. So many times whenever we need to perform several operations on binary tree, we need to traverse the tree. So what we do in traversal of a tree, each element of a binary tree is visited and processed exactly once in some predetermined sequence. So we'll repeat what we mean by a binary tree traversal. In a traversal of a binary tree, what we do is we go on visiting each element of a binary tree, and each element of a binary tree gets processed exactly once in a predetermined way or in a predetermined sequence. So what are those predetermined sequence and what are the kinds of tree traversals that we are going to discuss? So there are two general approaches to tree traversal, and these are depth first traversal and breadth first traversal. So today we are going to focus upon both kinds of traversal techniques. So let us begin with depth first traversal. So what is depth first traversal? In depth first traversal, actually the processing proceeds along a path from root node. So we always begin with root node. So in depth first traversal, what happens is the processing begins at root node through one of the children. So we traverse the root node, or we proceed in a way, in a path beginning from a root node through one child to the most distant descendant of that first child. After processing the most distant descendant of that first child, then and then only we go for processing a second child of a root node. What we mean by that? If I'm having a tree, so I'm having this node, then I'm having children of this root node. At the max, I may have 2 children because this is a binary tree. Then I may have children of children and so on. So what happens in first traversal is we begin from this root node and then we go to one of the children. So this is the child that we have selected. So via this child, what we do is we go to the most distant descendant of this child. What we mean by that? We'll go to the children of this child and we may process those children. And after processing all the children of this child, first child that we have selected of the root node, then only we go for processing of the next child. And the same process gets repeated for every child of this binary tree. So we are going to process all of the descendants of a child before we go to the next child. So unless we complete processing of one of the children, it is not possible for us to process the next child. This is how we may define the depth first traversal. In breadth first traversal, what happens is the processing proceeds horizontally. What we mean by horizontally? We process all the children of a binary tree level by level, beginning from the root node. So once again, if I am having this as the root node, and then if I am having few of the children of root node, and once again we are having the children for the nodes at level 1 and so on. Then in breadth-first traversal, what we do is, no doubt we will begin from the root node, but here we go on processing the nodes level by level. So we process all the children of this root node, that means we'll process this. Then we will process the children of children's in the next level, then next level and so on. So we go on processing the nodes level by level in breadth-first traversal. So we complete processing across the breadth of the tree and then we'll go to the next level. So this is the difference in depth-first traversal and breadth-first traversal. So in depth-first traversal, we pick one of the children and then we process till the distant descendant of that child, and then only we may process the next child after processing the first child that we have selected. So this is how actually we carry out the processing or traversal of binary tree. So depth-first traversal and breadth-first traversal. Now, if we look at the depth-first traversal, we are having three important kinds of traversal algorithms, or the sequence in which we may traverse the binary tree differs according to some sequence of processing the nodes. So accordingly, we are having pre-order depth-first traversal, in-order depth-first traversal and post-order depth-first traversal. So what is pre-order traversal? In pre-order traversal, what we do is, the root node gets processed first, followed by left subtree and then the right subtree. So in pre-order traversal, the sequence in which we are going to process our nodes is like root, left and then right. So we are going to process the root node first, then the left subtree and then the right subtree. So whenever I am saying it is a left subtree, being it is a binary tree, once again the processing would be in the same sequence. The root of the subtree, then left subtree of that and then the right subtree of that. And this is how we proceed with the traversal of the nodes. So this is what we mean by pre-order traversal. Root, left, right is the sequence. In order traversal, what we do is, after the complete processing of the left subtree, the root gets processed, and then after processing the root, we go for processing of right subtree. So the sequence is, left subtree gets processed first, then root of the tree and then right subtree. So this is how in-order processing takes place. In post-order processing, what we do is, we process the left and right subtrees first and then we go for processing of the root node. So the sequence is like, left subtree gets processed first, then right subtree gets processed and then we process the root node. Ultimately, whichever may be the sequence of traversal, pre-order, in-order or post-order, we make sure that each and every node in my binary tree gets processed. The sequence might be different. Now, let us see pictorially the same thing: pre-order traversal, in-order traversal and post-order traversal. So this is pre-order traversal. So see here, similar to that of we defined earlier, what we are going to do is, we are going to process the root node first, then we are going to process the left subtree and then we are going to process right subtree. So we are following the sequence 1, 2, 3, root, left subtree and right subtree. in-order traversal, what we are going to do is we are going to process left subtree first, then we are going to process the root node, and then we are going to process the right subtree. So the sequence is 1, that is left subtree, then 2, that is the root node, and then 3, that is the right subtree. In case of post-order traversal, what we are going to do? What is the sequence? In post-order traversal, the sequence is we are going to process the left subtree first, then the right subtree, and then the root. So see the sequence: 1, that is left subtree, 2, that is right subtree, and then 3, that is the root node. So this is post-order traversal. Now, as I mentioned earlier, you might have gone through the recursive algorithms to perform pre-order traversal, in-order traversal, and the post-order traversal. Have you gone through the recursive algorithms to carry out these tasks? Yes or no? Have you gone through the recursive algorithms earlier to carry out these tasks? Yes? Anybody? I want answer from you. Have you gone through the recursive algorithms? Hello? Am I audible? Yes or no? Hello? Am I audible?
Yes, ma'am.
Then why you are not answering my question? Have you gone through earlier the recursive algorithms for tree traversals?
Yes.
Yes. So all are aware of how to perform recursive operation or recursively how to implement the traversal algorithm. So let us go through one example of a pre-order traversal. So this is one tree. Are you able to see my screen?
Yes.
So we are having one binary tree on our screen with 6 nodes, right? If I would like to perform pre-order traversal, what is the sequence that I need to follow? It is pre-order. So I need to process root node first, then the left subtree, and then the right subtree. So if for this tree, if I would like to process the nodes in pre-order fashion, then I'll be processing the root node first. So A gets processed first. Then I'll go for this left subtree. Now, whenever I'm processing this left subtree, once again I need to follow the same sequence. So I'll be processing first, and then I'll go for the left subtree of this B, and then right subtree of this B. So I'll go for left subtree of B. So in this left subtree, I'm having a single node, and that is the root node right now. So I'll be processing that root node. I do not have left or right subtrees for this C, and hence I have processed left subtree of this B. So I'll move on to the right subtree. So next I'll be processing this B. So I have completed processing of this subtree B. So I'll move on to the right subtree of A. So while processing this right subtree, once again, the sequence to be followed is root left right. So I'll be processing this root. Then there is no left subtree, so nothing to do. So I will move to the right subtree and I'll be processing the right subtree. Ultimately, I am having this pre-order traversal sequence: A, B, C, D, E and F. Am I correct?
Yes.
Fine. So this is how our pre-order traversal works. Okay. Now, let us proceed to the algorithm, recursive algorithm for pre-order traversal. You might have gone through this kind of recursive algorithm earlier. So this is algorithm for pre-order traversal, and what is the argument that we are sending is the address of the root node of our binary tree. So in this pre-order traversal, our sequence of processing is root, then left subtree and then right subtree. Correct? So how we have written this algorithm? In this algorithm, we are checking if root is not null. That means we are checking that whether our tree is empty or not. If our tree is not empty, then we are going to process the root node. So we are having here the statement process root node. So after processing the root node, what we need to do is we need to recursively call the same algorithm pre-order with the address of left subtree. So we are having here a call pre-order with the address of left subtree. So it will once again enter into the same algorithm and carries out the task for the left subtree. After we done with the left subtree, we are having one more call, recursive call to the same algorithm pre-order with the address of right subtree. And then this is the end if for our if. So this if condition will check whether my root node is null. If it is not null, then we are going to process the root node. Then we are going to recursively call the same algorithm with the address of the left subtree, and we are calling the same algorithm with address of right subtree. If my tree is empty, I am not going to do anything. So this is the simple way how our pre-order traversal can be implemented in a recursive fashion. This is very simple, straightforward algorithm. You might have gone through this. Am I correct?
Yes.
Fine. Now, let us see one example. Once again, the same example, same tree we have. So we are having 6 nodes and these are arranged in some fashion. So A, B, C, D, E, F is the data part of that node, respective node. And whatever numbers, those I have depicted here, let us assume that these are the addresses of the nodes in memory. Now we know how actually a node of a binary tree gets stored in memory. So this is how the node gets stored. So this is the data part. So whatever may be the data that I would like to store in this node, I'll be storing that data here. Here, for simplicity, we are having a simple single character that we have stored as data. But the data may be anything, or this data may be a pointer pointing to actually some kind of a data, right? So I'm having here the data and I'm having 2 partitions, 2 more elements. Those are being stored in a single node, and this represents the address of left subtree, and this represents the address of right subtree. So what we mean by address of left subtree and right subtree here? The address of a node which is placed towards left, and the address of the node which is placed towards right. So this is how actually we are storing a node of a binary tree in memory, right? So if we look at this node A, right, base address of this node is 100, okay, and left subtree is placed at address 200 and right subtree is placed at address 600. That is how we are interpreting this node A. Is that clear? Yes?
Yes, ma'am.
Fine. Now, what next we are going to do is, just we are going to simulate the calls, recursive calls for this pre-order traversal algorithm. We would like to traverse this tree in pre-order fashion. We are having the recursive algorithm, so let us try to simulate the calls, recursive calls for this pre-order traversal algorithm, right? So once again, I'll be explaining this algorithm. First of all, we are checking whether our tree is empty. If it is not empty, we are going to process the root node. Then we are recursively calling the same algorithm for left subtree, and then we are going to recursively call the algorithm for right subtree. Okay. Now, please note that whatever is this state, process root, right? So as I mentioned, we may have different applications for this traversal algorithm. So depending on the application, why we are traversing the tree, this definition of this process would be different. Am I correct? Am I correct? Depending on
Yes.
whatever is the application under consideration, definition of this process may change. Right now, let us assume that processing a node simply means just printing the data in that node. Is that correct? So whenever I say that process A, what I am trying to do is simply I am trying to print that data A. Okay? But depending on the application, this processing may be different. If, say for example, if I am storing some numeric data in each node, and if I would like to sum up all that data, then my processing would be different. So for the sake of simplicity, right now we are assuming that processing the root node means simply printing the data in root node. So once again, I am emphasizing, depending on the application under consideration, the definition of my process is different. Okay, right now I am processing the node means I am printing the data from that node. Okay, so let us proceed with the simulation. So the first call of this pre-order algorithm will be pre-order with address of this root node. So address of this root node is 100. So this is how we can simulate, or how we can show the recursive calls, right, to this pre-order algorithm whenever we are traversing this given tree. So see here, the first call of pre-order is pre-order with address of the root node, that is 100. Correct? So I'll be entering into this algorithm. So what I'll check is whether my root is null. So right now my root is not null because it is storing the address 100. So as my tree is not empty, my root is not null, I'll be entering into this if. So what next? I'm having here the statement process root. So as I mentioned, what is the definition for my process? My process definition is whatever is this data that is stored at this place, I just would like to print that. So right now my root contains the address 100. So I'll be processing the data stored at this address 100, and processing means simply I'll be printing the data. So I have processed this root node A. So after processing this, the next statement that I would like to execute is preorder left subtree. So this is once again a recursive call. I am calling the algorithm once again with new address, and that is address of left subtree of my root. So right now my root is 100 and the left subtree is having the address 200. So I am calling this algorithm now preorder with address 200. Am I correct? Yes?
Yes, ma'am.
Fine. So we are having this one more call to preorder. So I am calling preorder with new address of the left subtree, that is 200. This is the address of the left subtree. Now once again I'll be entering into this algorithm. I'll be checking. Now my root becomes 200, right? So I'll be checking whether it is not null. Yes, if it is not null. So what I'll do is I'll enter into this, and once again I come across this instruction, that is process root. So right now my root is 200. So I'll be processing that. So processing means I'll be printing the data stored at this location 200. So the data at this location 200 is B, and that is why I am processing that. So in my sequence I have processed that node, that is B. What next? After doing this, I'll be having once again the statement, that is preorder left subtree. So I am at this position. So who is the left subtree now? This. And what is the address of my left subtree? That is 300. So I am having one more call to preorder with address 300 now. So once again I'll be entering into this algorithm with now root equal to 300. So root is not null. So once again I'll be processing my root. Processing my root means simply I'll be printing whatever is stored in this node. So that is C. So I have processed that node. After processing, I'll be calling preorder left subtree. Now I have reached to this node. So whatever is the left subtree, I'll be calling preorder algorithm with address of left subtree. Now the address of left subtree is null. So I am having this call preorder with address as null. So once again I'll be entering into this algorithm with root as null. So whenever I test this condition, if root is not null, this is not satisfied because my root is null. So what will happen? It will come out from this. So for this call, I am not going to execute anything and I will return back to my calling function. So who called this preorder null? This preorder 300 called. Correct? No? This preorder 300 called this preorder null. So after executing this, means after not doing anything, I'll be returning back to this call preorder 300. Correct? So in this preorder 300, I had already done this. I have now done this, and that is why I need to call preorder write subtree from this call preorder 300. So in this call I have reached to this statement, and now I am calling preorder with write subtree of this 300. So right now write subtree of this 300 is once again null. So I am calling this preorder null. So after calling this preorder null, what will happen? Once again I'll be entering into this. As my root is null, this may not be processed or executed, and I will go back into the calling function. So my preorder 300 call is complete. I have done this, this and this. So everything is done. So preorder 300 call is completed, and it will go back into the earlier call preorder 200. So in preorder 200, I have done with this left subtree processing, right? So I need to execute now the next statement in preorder 200, and the next statement in preorder 200 is I have done with this. So I need to call now preorder with the address of write subtree, and that is 400. Are you getting me? Yes?
Yes,
Are you
ma'am.
getting me? Please see here
Yes.
how actually the recursive calls are being executed. Very important to understand. So whenever I am calling now preorder with this address 400, what will happen? I'll be entering into this call, this algorithm. I'll check whether root is not null. Yes, root is not null. So I'll be processing this root. So processing this root means I'll be processing whatever is stored at this location 400. Right? So I'll be processing this node, and I'll be printing the value D. So I have done till this, process this node. After processing this node, I need to call preorder with the left subtree of this node. So I am calling here preorder with the left subtree address. In this situation, that is null. So once again, there would be a call, but no processing because root is null, and it will go back to the calling function. So who called this? This preorder 400. Okay, and which was this call? This left subtree. So I am returning back to this statement in the call preorder 400. So whenever I reached to this call, I'll be once again calling preorder with the address of write subtree. So who is the write subtree here? Once again, null. So I'll be calling preorder once again with the null value. Once again it will enter. It is root is null, so nothing needs to be done. So after processing, it will go back. Where it will go? It will go into the processing of 400. Right? Preorder 400. Now in preorder 400, we have done with processing of the node, traversal of the left subtree, and preorder traversal of the right subtree. So we are done with now this preorder 400, and that is why it will jump back. It will return back to the calling function. So what was the calling function? It was preorder 200. That called this preorder 400, right? So after processing this, this will return back to preorder 200, and ultimately, as everything is done in this call of preorder 200, ultimately we are switching back, okay, to this preorder hundreds call. So whenever we reach to preorder hundreds call, what we interpret here is we had already processed this node. Now we have done with preorder left subtree, Correct? So we have done this and this with respect to this root node 100, and now we are having a call preorder write subtree for this root node, and this is how we are going to call now preorder with the address 600. Am I correct? Yes?
Yes, sir.
Are
Yes, madam,
you
understood.
getting me? Yes. So
Yes.
this is how we are supposed to simulate the calls whenever we talk about any recursive algorithm, because this will help us to understand what actually is happening. Right? So whenever we are calling this preorder 600, what will happen? I'll be entering into this call. Root is not null. So we are supposed to process this root node of this subtree. That means we are processing this E now. So E gets processed. So we have printed here E, and then we are having preorder left subtree. So for this node, I'm not having any left subtree. So I'll be having a call preorder with null. Right? So I'll be calling preorder with null value. So this may not be processed. Correct? And I'll return back to the calling function, that is preorder 600. So I have done with this, I have done with this. So I need to call preorder write subtree. So I'm having here the call preorder with address of the write subtree, that is 700. So I'll be entering into this. I'll be checking whether my root is not null. Yes, it is not null. So I'll be processing the root node. So processing of the root node, meaning I'll be processing the data stored in this root node. That is the write subtree. So I'll be processing this F. So I'm having here F in the list. Okay. So after processing, what I need to do is I need to process the left subtree. Now for this node, I do not have any left subtree. So call is with null. So nothing needs to be done. Once again, it will go back into the calling function. Then it will call the same algorithm preorder with write subtree. Here write subtree is also null. So nothing needs to be done. It will go back. Then I have done with this preorder 700. So it will go back to the calling function. So who called this? Preorder 600 called this. So it will return into preorder 600. So obviously this is completed in preorder 600. Write subtree has been processed. So once again, nothing needs to be done. So go back to the calling function. So who called this preorder 600? Preorder 100 called this. So we are returning back to preorder 100. Now, whenever we return back to preorder 100, we come to understand that we have done this. We have processed left subtree, and now we have processed right subtree, and that is how we have completed this traversal task, right? And this may once again go back to the calling program. So we are done. So our traversal, preorder traversal is like this: A, B, C, D, E, F. A, B, C, D, E, F. And this is how my recursive calls will work. Is there any doubt so far? Yes?
No, ma'am.
May I proceed?
Yes.
So I hope you were knowing this recursive algorithm. Recursive algorithms are really very simple, right? But we should understand how actually they are being processed internally, right? And this is the tree kind of a structure that is actually depicting the individual recursive calls with respective addresses of the nodes, right? So I hope that you must have understood how actually this has been processed. And please remember that whenever we are calling any recursive algorithm, my compiler internally is using stack to store the stack frames, right? And these stack frames are actually storing whatever is the information that is required, right, prior to entering into the new call. So that information is being stored onto the stack, right? So we are pushing the information onto the stack with respect to every recursive call for the algorithm, and whenever we come back, we are going to pop that information. So internally, whenever the recursive algorithm is being executed, compiler internally is using stack to store this kind of intermediate information that needs to be remembered at the time of every call. I hope you must have understood the concepts. So let me proceed with the next kind of depth first traversal, and that is in order traversal. So as we have discussed earlier, in case of in order traversal, we are having the sequence to be followed, like first process the left subtree, then process the root node, and then process the right subtree. So once again we are having the same tree as an example, and we are going to perform in order traversal with respect to this tree. So obviously we are going to process the left subtree first. So in this left subtree, I am having one more left subtree. So whenever I say that I would like to process this left subtree, I need to think of whichever is the left subtree of this subtree. So this is the left subtree, right? So this is the left subtree without having any children. So I'll be processing this node first. So I'll be processing C first, then I'll go for root. So I'll be processing this B, then I'll go for right subtree. So I'll be processing this D because there is no child for this D. Okay. After completing processing of this left subtree, I'll go to process root node. So this is how I'm going to process A. Then I'll go to the right subtree. In this right subtree, I'm not having any left subtree, so I'll be processing this E, and then I'll go for right subtree, and then I'll be processing this F. So overall, this is how I am processing my tree in order fashion. So what I'll be processing first, I'll begin from this. So I'll be processing first this C, then I'll be processing this B, then this D, then I'll go for root node A, then I'll process this subtree. I'm not having here anything here, right? So I'll be processing this E, and then I'll be processing F, and I'll return back. So my processing order in order traversal is C, B, D, A, E, F. So process left subtree, then process root node, and then process right subtree. Is that correct? Any doubt so
No,
far?
ma'am.
May I proceed?
Yes, ma'am.
Now, similar way, it is possible to write the algorithm for in-order traversal. So once again, for in-order traversal, we are sending address of the root node as the argument. So here also we are checking whether our tree is empty. So if our tree is not empty, we are going to call the same algorithm in order with address of with the address of left subtree. So after processing in order fashion our entire left subtree, we are going to process the root node. And after processing the root node, we are once again going to call recursively in order traversal algorithm with address of right subtree. Correct? Once again, let me remind that this process may be anything depending on our application. How we are going to make use of that data stored in that root node, and whatever kind of processing we would like to have, accordingly we are having defined this process function. Am I correct? So we are maintaining the sequence left, root, right. So we are processing left subtree in order fashion, then we are processing the root node, and then we are processing right subtree in order fashion. And please remember, this left subtree and right subtree itself is a tree. So recursively we go on processing these trees in order fashion. Am I correct? Yes.
Yes.
So I would give you the homework now. Similar to how we have simulated the calls for pre-order traversal, right? You are supposed to take the same tree as example, okay? And you need to draw a tree kind of a structure depicting the recursive calls for in-order traversal algorithm, similar to whatever we did earlier for pre-order. So I'm giving you this exercise. So whatever we have done here, right, to simulate the calls, recursive calls for pre-order traversal, you are supposed to prepare such kind of tree diagram that will depict the calls for in-order traversal. Am I correct? Right? So you should come up with such kind of a simulated structure for in-order traversal for this recursive algorithm. May I proceed?
Yes, ma'am.
So the next kind of algorithm is post-order traversal. So as we know, in post-order traversal, the sequence to be followed is we are supposed to process left subtree first, then right subtree, and then root. So if once again we are having the same tree, okay, then if I would like to perform post-order traversal for this tree, to traverse each and every node in this tree, what we are going to do is we are going to process this left subtree first, then we are going to process this right subtree, and then we are going to process this root node. So this is the sequence of processing. Now, whenever I say that I want to process this left subtree in post order way, then what I need to do? This is once again a binary tree. So for this binary tree, I need to perform post order traversal. So in this case, what I need to do is post order for this tree. So I need to process this node first, left subtree, then I need to process right subtree, and then I need to process root. Correct? Whenever I am processing this right subtree in post order fashion, once again I need to follow the same rule. So first I need to process the left subtree. So I am not having this left subtree here. So I'll process this right subtree, and then I'll process the root node. And after processing this and this, I'll go for the actual root node of my original tree. So let us see now how it works. So first this left subtree gets processed, then this right subtree gets processed, and then the root node. So if I have completed this left subtree processing, then it will go to the right subtree. So in this right subtree, I am not having here the left subtree for this right subtree. So I'll be processing this F first in this right subtree, and then the root node, that is E, and then I'll be processing A. Right? So the sequence of post order traversal is like this. I'll be processing C, then I'll be processing D, then I'll go for root node, then I'll go for the root node of the entire tree. Sorry, I'll be going to the right side, right subtree of the entire tree. So in this right subtree, I'll process F, then I'll process E, and at the end, I'll be processing the actual root node of my tree. So the post order traversal is like C, D, B, F, E, and A. Am I correct? Yes. Have you understood the thing?
Yes, ma'am.
So let us proceed with the algorithm, recursive algorithm for post-order traversal. So on the similar lines, we are having the simple post-order traversal algorithm in a recursive fashion. So here also we are sending address of the root node to this algorithm. We are checking whether the root is empty. If it is not, then we are calling the same algorithm with left subtree, then we'll call the same algorithm with address of right subtree, and then we are going to process the root node. So once again, I am giving you the exercise for the same example tree. Try to come up with a simulation of the calls to this recursive algorithm to better understand the concept and how recursion works. Right? So one more exercise. For post-order traversal also, you are supposed to come up with a simulation depicting the recursive calls to the post-order traversal algorithm for the given example. Right? So I hope you have understood the traversal algorithms, and typically the depth first traversal algorithms written as the recursive, written in recursive fashion. Right? Comparatively, the recursive algorithms are easy to write, but sometimes it may be difficult to understand. So try to simulate the calls and try to understand how this recursion is working. So now let us proceed with non-recursive kinds of algorithms. We talked about recursive algorithms, and writing a recursive algorithm is very much easy if we look at these three kinds of algorithms. Now, if I ask you to write the non-recursive algorithm for pre-order traversal, then can you give me a logic? I do not want to use recursion. So obviously, if I do not want to use recursion, I need to use some iterative process so that I can traverse each and every node in my tree in pre-order fashion. So pre-order means what? What is the sequence in pre-order? In pre-order, what we do? We process the root node, then we go for left subtree, and then we go for the right subtree. So root, then left tree, and then right tree. That is the sequence. Now, anybody who can suggest the process how we can use non-recursive or how we can write non-recursive algorithm for pre-order traversal. Please speak up. I want logic from you. We are having one example tree here. So what should I do? Yes, anybody? Yes. What should I do? This is pre-order traversal. So the sequence I need to, in this particular example, I need to process this A first. Then I need to go to the left subtree. So in this left subtree, once again, I need to process the root node first. Then I need to go to the left subtree. So whenever I go to the left subtree here, only one node is there, so I need to process this. And then I need to go to the right subtree of this B. And then I need to process this. And after complete processing of this, I need to go to the right subtree of this A. Then I need to go to left subtree of E. In this case, we do not have left subtree. Then ultimately, I'll be going to the right subtree and I'll process this. So this is what I need to do. I do not want to use recursion. So how to write the code or algorithm? Please tell me, apply your brain. Yes, anybody? This is really very interesting and this will help you to build your logic. What should I do? Yes? Anybody? May I need to use any other kind of data structure here? I'm giving you some hints. Whether I should go for some kind of data structure here? Other data structure? Yes. Nobody can think in that direction. It's surprising. Yes. Please pick up.
Hello.
Yes.
Ma'am, can we use Q?
Q. Why Q?
So we can go on add elements, and as it is first come first serve, so we can get the pre-order.
Okay. But instead of Q, see, this is a depth first traversal, correct? And what we need to do is whatever we store at the end, we need to process that first in this situation. Let me tell you how. Okay. See, whenever I have been provided with this address of the root node 100, I am having that address with me. So no doubt it is possible for me to directly process the root node. No issues, right? And after processing this root node, what I'll do is I'll go for the left subtree, right? So whenever I'll go for this left subtree, right, I'll be processing this left subtree entirely, and then I need to come back to the right subtree. But after processing this left subtree, or while processing this left subtree, what I need to do earlier is I need to remember the address of this right node somewhere. So somewhere I need to store that address where I need to go after processing this left subtree. So I need to remember something, and to remember that the best data structure in this situation to be used is stack and not the queue. And let me tell you why with this example, right? So let me give you the algorithm, non-recursive algorithm for pre-order traversal. So this is the non-recursive algorithm. You may not find this algorithm, right, in your prescribed books maybe. So please see this algorithm and try to understand this algorithm carefully. Many times in interviews you may be asked, right, because recursive algorithm is somewhat easier to implement also and easier to remember also. Okay, but this is somewhat tricky how we can write the non-recursive algorithms, and many times the big companies are asking you such kind of tricky questions. So how to implement the traversal algorithms in non-recursive fashion? So you should be able to give the logic as well as you should be able to write the algorithm, and if asked for in the coding round, you might be asked to implement this also, right? But right now forget about implementation. Let us try to understand actually the logic behind. Okay, so what actually we are going to do? We are going to call this algorithm with the address of the root node. So in this case, address of the root node is 100. Okay, now as I mentioned, we are going to make use of a stack. So I am having here a call to a function, ADT function of the stack. So please remember, we have created the stack earlier, or rather we have created the ADT for the stack earlier, and we have learned how to create the ADT for the stack. So let us assume that we are having that ADT with us, right? So we are calling simply the function from that ADT, and we are creating a stack. So creating a stack meaning will be creating the empty stack. Okay, and this function will return the address of top of the stack. Okay, fine. Now what next we are going to do is we are having one variable pointer, and that is equal to root. So root actually right now contains this address 100. So we are declaring one more pointer, PTR, that is actually pointing to this root node. So this pointer is pointing to this root node, meaning this pointer also stores the address of this root node, that is 100. So set pointer to root means now I am having one more pointer that is also storing the address of the root node. Now what next I'll do is I am having one iterative loop. As I mentioned, as we are not using recursion, we should have some way to iterate through, some way to repeat these steps for entire tree. Okay, so in this loop we are checking whether pointer not null. So once again what we are checking here, whether our pointer that is pointing to the node is empty. That means whether it is storing null. So whether we are referring to any empty tree or not. So if my pointer is not null, so in this situation my pointer is having the value stored as address of A and that is 100. So it is not null. So I'll be entering into this loop and I'll be processing this pointer. So processing this pointer, once again, for the sake of simplicity, we are saying that this process function is actually printing the data stored at that node. So process pointer means I am processing the data here and I am printing that data. So I have processed this node A. Okay, fine. What next? After processing this, what I need to do is I need to go for processing this left subtree. But prior to going to the left subtree, what I need to do is I need to make the provision that after processing this left subtree, where I would like to go? I would like to go to the right subtree. And what needs to be done is I need to remember where to jump after processing this left subtree. And for that reason, what we are trying to do is we are going to store this address of the right child of this root node somewhere. And that somewhere is our stack that we are using here as a programmer's tool, right? So what we are going to do next is after processing this root node, we are checking whether there exists any right child. So if there exists the right child, what I'll do is I'll push this address onto the stack. So I'm calling once again the function from my stack ADT, and that is push stack that we have created. And what we are going to push? We are going to push pointer R child. So right now my pointer is pointing to this node, right? So this node is having this as the right child and this as the left child. So what I'm trying to do is I'm trying to push this right child of this node onto the stack. So what is my condition? If there exists the right child for this node, then remember the address of this right child. And to remember this address, I am making use of the stack. And what I am pushing onto the stack? I am pushing onto the stack this address of right child. So address of the right child here is 600. So that address I am going to push onto the stack. Right? So this is actually the address of my element or the node E, where I have stored this E. So I'm pushing address, I'm not pushing data. I'm pushing address of this node. Okay, with this statement. Now, I have pushed right child onto the stack. Why? Because afterwards, I'm going to make use of that. Right? When I'm going to make use of that? After processing this left subtree. Okay? So, what next? I'll check whether there exists a left subtree. So if there is a left child, so how I'm going to check that? I'm having this pointer pointing to this node. So I'll check whether pointer L child is null. If it is not null, meaning there is a left subtree present. So if it is not null, then what I am going to do is I am going to update my pointer PTR such that it will now point to this left child. So pointer left child is address 200. So what I'll do is I will now use this pointer such that now my pointer is pointing to the left child of earlier root. So left child of this A is 200. So my pointer gets updated with that address. So my pointer is now pointing to this node. So this is now the root node, correct, of my subtree, right? So if pointer L child is not null, that means there exists the left subtree. Simply what we need to do is we need to update this pointer with the address of the left subtree. So now my pointer will contain this address 200. So I am done with this. Nothing to or no need to bother about this else part. So I have reached to end loop. Now in the next iteration of this loop, my pointer once again will be checked whether it is empty or not. Now pointer is pointing to this subtree now and pointer is not null. So what I'll do next is I'll be processing whatever is stored at that pointer, whatever is stored at the node pointed by that pointer. So what is stored over there? It is B. So I'll be processing this B. So I'm traversing that node. I'm processing that B. Okay. Now, after processing this node, once again, the same process I need to follow. So this is preorder. So after processing the root node, I need to go to the left node or the left subtree. But before going to the left subtree, what I should do is I should remember the address of the right subtree, okay, of this node. So what I'll do is once again, this is now my pointer. So once again, I'll check whether there exists a right subtree. For this node, I'm having a right subtree. So what I'll do is simply I will push this address 400 now, okay, on my stack. So I'll be having now this 400 pushed onto the stack. So this 400 is nothing but the node which contains the value D. So I have pushed this node onto the stack. Okay, so I'm done with this. What next? I'll check whether there exists a left subtree. Yes, there exists the left subtree. So what I'll do is simply now I'll update this pointer such that this pointer will point to this node. So my pointer will point to the left subtree of earlier pointer. So now my pointer contains this address 300. Correct? Now, nothing to worry about this else part. No need to worry about this else part. So I have reached to the end loop. So once again, I'll be iterating through. Now, in this next iteration, once again, I'll check whether pointer is not null. Yes, pointer is not null. It contains right now the value 300. That is address of this node. Okay. So what I'll do is I'll process this node. I'll enter into this. I'll process this node. So C gets processed. Okay. Now, after processing this C, what will happen? I will check whether there exists any right child. Now, for this C, there is no right child. Okay. So pointer R child is null. So this will not be executed. So we do not have anything to remember. We do not have anything to push onto the stack. So we'll go to the next statement. So this statement will check whether this node, pointer is right now pointing to this. So whether this node is having the left child. So right now the left child is also null. Correct? So if my left child is null, then what it will do? So it will enter into this part. So if left child is null, Then what needs to be processed? Meaning this has been processed. So what I'll do is I will pop now one element from stack. So what is there onto the stack? So I'll be popping. Popping means I'll be removing this from the stack. And whatever I am popping, this address gets assigned to my variable PTR. So now what will happen? My PTR will point to this node with address 400. So my PTR is now pointing to this node with address 400. Am I correct? Are you getting me?
Yes, ma'am.
Okay. So now I'll be iterating through once again. So pointer is not null. So this pointer is not null. So what will happen? I'll be processing this D. Is that correct? So I'll be processing this D. So D will come into my sequence of process nodes. I have processed this D. What next? It may happen that for this node I am having some subtree. It may happen. So I need to check that. So once again, for this node, I'll be checking whether there exists any right child. For this node, I do not have any right child. So do not worry about this. Once again, I'll check whether this node is having any left child. Right now, there is no left child for this node. So I'll not do this. Okay, so I'll be entering into this part. So what I need to do is, as I'm not having any left child or right child here, what I need to do is I need to pop one more element from my stack. So whenever I execute this statement, set pointer to pop stack stack, what will happen? Whatever is the element at the top of the stack. Right now I am having this element at top of the stack. So this element gets removed from the stack, right? And this address 600 will be assigned to this variable PTR. So now my pointer will point to this node that I remembered earlier. And see, this is the way how we are getting or how we are making use of my stack to store the intermediate values. So now I am having 600 stored as the value of pointer. Correct? So once again I'll be iterating through. So pointer is not null. Yes, it is not null. So what I'll do is I'll process this E. So here I'll be appending that E in my processed list. So I have processed this E. What next? The same procedure follows. So I'll be checking whether there exists any right child. Yes, there is a right child. So what I'll do? I'll push address of this right child onto this stack. So I'll be pushing now. So right now my stack is empty. I have removed everything from this stack. Okay. So I'll be pushing now this 700, which is the address of this node F onto this stack. Okay. Now what next I'll do? I have remembered the right child where I need to go later. So I'll check now whether there exists any left child. Now in this case, I do not have any left child. So this statement will not be executed. As L child for this pointer is null, I'll be executing this statement now. And this statement is set pointer to pop stack stack. So whatever is at the top of the stack, I'm going to pop that. Meaning I'm going to remove that. And in this node pointed by this PTR. So I have processed this node F. Okay, and I have printed that value. What next? I'll check whether there exists any right child. So right now I am not having any right child for this node F. So nothing to push onto the stack. Then I'll check whether there exists any left child. I do not have any left child also. So my left child is also null. So what I am doing here, I am having entered into this else part because there is no left child. So I am popping one element from the stack. See here, as I am popping the element from the stack, my stack is empty right now. I do not have anything to return, and that is why my pointer will contain at the end the null value. Because my stack is not having anything to return, so it will return the null value. So pointer will become null, and as my pointer becomes null, that means in the next iteration pointer is null, so it will not enter into this loop, and I am done with my algorithm. So I have processed, please see here, I have processed A, B, C, then D, then E, and then F. And simply what I have done is, whenever I am traversing any node, right, first I'll check whether there exists any right subtree. If there exists any right subtree, push address of that node onto the stack. And the reason is because afterwards we need to reach to that node, and somehow we need to remember that address, and that is why we are storing address of the right node onto the stack. And then we proceed with processing of the left subtree, and the similar process we need to follow. So wherever we are having the right subtree, we are going to push those addresses onto the stack. Correct? And simply whenever we are having no left subtree, then one by one we go on popping the elements, the addresses from the stack, so that it will indicate that we are done with the left subtree processing, and now we should go to the processing of the right subtree. That's all. So I hope you must have understood how actually I can write a non-recursive algorithm. And to write non-recursive algorithm, I need to use some kind of iterative mechanism. Here we are using a loop, okay, to iterate through, and obviously we need to remember few addresses, intermediate addresses of the nodes, and that is why we are making use of this stack. Is there any doubt? If you have any doubts, please let me know. Yes, any doubt? Any doubt? Have you understood the algorithm? And how we made use of a stack? Yes? Any doubts so far? Any doubt? Please let me know.
No, ma'am.
Have you understood?
Yes.
So whether you got something that is helpful, value addition to your earlier knowledge?
Yes.
Yes, ma'am.
This is how you should be able to devise new algorithms, new logic. So now let us proceed to the next kind of non-recursive algorithm, and that is the in-order traversal. Now tell me the logic, how in-order traversal can be implemented. In-order traversal. So the sequence is, in order means first left subtree, then root, and then we are supposed to process the right subtree. Barabar na? So what would be the logic? Just think on. What we need to do? We need to process this left subtree, then we need to go to the root, and then we need to go to the right. बरोबर ना? त्यामुळे जेव्हा मी इथे मला सुरुवातीला काय माहिती आहे, फक्त ऍड्रेस हा माहिती आहे रूटचा. बरोबर? आता मला रूट प्रोसेस करायचं नाही आहे. What I need to do? I need to process the left subtree. So I need to go first to the left subtree. But as I am going to the left subtree, what I need to remember? I need to remember address of this, no? Because after processing this, I need to come back to this. So I need to remember this address. Barabar?
Yes.
So once again, I need to make use of stack to remember these addresses, where I need to jump afterwards. Correct? So please go through this algorithm for in-order traversal using non-recursive algorithm. So here also we are making use of a stack. So we'll be creating a stack, and initially our pointer will point to the root node. Okay. Now what we have is, see, this is in-order traversal. So we begin from this. What next? We need to process this left subtree, na? So whenever we say that we need to process this left subtree, then this is the root of the left subtree. So once again we need to think. We are not going to process this first, na? We need to go to this node, left subtree of this. So we need to remember this also, and we need to reach to this. Am I correct?
Yes,
And
ma'am.
wherever there is no left subtree, right, then we are going to process this. Am I right? So after beginning from this actual root node, what we need to do is we need to reach to a node where this left subtree is null. Until that, whatever comes in my path, I need to push all those addresses onto the stack so that I can remember afterwards where to jump. Am I correct? So this logic can be implemented like this. See here, we are having one loop. So initially my pointer is pointing to this root node. Okay. So if my tree is not empty, that means loop pointer not null. So if my pointer is not null, what I am going to do? I am going to remember first this 100. Barabar na? So I have created a stack, and I'll be remembering this 100 initially. Okay, so I'm pushing it onto the stack. What next? I'll go to the left child. So set pointer to pointer L child. So I'm shifting my pointer to this left child. So my pointer will now point to this. Is that correct? I'm having this loop. So pointer is not null. So I have not yet reached to the leaf node. Okay. So pointer is not null. So what needs to be done? Once again, I need to go to the left. But before going to the left, I need to remember this. So I'll be pushing this 200 also onto the stack. Right? What next? Set pointer to pointer L child. So pointer now points to this left child. So pointer is now having the address 300. Okay, so pointer is not null. Yes, it is not null. So what I'll do? I'll push that also onto the stack. So I'll push that address also onto the stack. So I'll be pushing this 300 also onto the stack. What next? Set pointer to pointer L child. So what is L child of this C? It is null, right? So my pointer is now having the value null. So whenever I go for checking this condition, now my pointer becomes null, right? So I'll be coming out from the loop and I'll reach to this statement now. Okay, so after coming out from this loop, what I'll do? I have reached to the leaf node now in this part. So what I'll do is I will pop the top element from my stack. Okay, and pointer is now storing that address. So I'll be removing this address and my pointer is now storing that address. So my pointer is once again pointing to this node. So whenever my pointer is pointing to this node, what I'll do? What I'll do next? Please see here. This is really very important logic. Right? So my pointer is not null now. Yes, it is not null. So what I'll do is I'll process this because I have checked that there is no left child for this. So I need to process this. So I'll be processing this C. So in my list, I'll be processing this C. What next? It may happen that for this C, I'm having some right subtree here. So I need to check for that. Is that correct? There is no left child. So I have processed this in order fashion. But it may happen that I'm having the right subtree here. So for that, I'm having here the statement if pointer rchild not null. So if I'm not having this right child of this node, okay, right now I'm not having right child of this node, right? So if I'm not having the right child of this node, then I'll go to this. And if I'm having some right subtree here, then I need to go through this. Okay, so right now let us forget about this part and let us go to this statement, set pointer to pop stack stack. So I'm not having any right child here, so nothing needs to be done. And what I need to do is I need to pop the element from the stack, and the element on top of the stack is 200. So now my pointer will point to this 200. Okay, so I have processed this and now my pointer is pointing to this 200. So I am having here end loop. So if my pointer is not null, yes, it is not null, it is having the address 200 right now. So I am going to process this node. So I'll be processing this B. Okay, now I have processed this. Now please see here. Now this node is having the right child. So I have processed this B and I'll be checking whether it is having the right child. Okay, so if it is having the right child, then what I need to do is I need to carry out the entire process once again to process this right subtree in order fashion. And that is why what I am going to do is, if my pointer rchild is not null, in this case it is 400, set pointer to pointer rchild. So my pointer is now pointing to this node with address 400. And with this as the root node, listen carefully, with this as the root node, I am going to do this entire process once again. So I am having here the statement go to R step. So what is R step? R step is a label for this statement. So I am jumping to this statement. Okay, and what I am going to follow next is I am having once again the loop. So same process. So I may have here the entire subtree present. So to carry out the in-order traversal for this entire subtree, if there is any subtree, then I need to follow all those steps as it is. Okay, pointer is pointing to this 400. So loop pointer not null. Yes, it is not null. So what I'll do is I'll push that 400 onto the stack, because at this instance I do not know whether this is having any left subchild or right child. So I am pushing this 400 onto the stack. Now what I'll do next is set pointer to pointer L child. So for this L child is right now null. So pointer will contain the null value, and as my pointer has become null, it will come out from this loop, because there is nothing below this tree, below this node. So what I'll do next is, right now my pointer is null. So what I'll do is set pointer to pop stack. So what is there on top of the stack? Right now I am having this 400 on top of the stack. So I will pop this, and once again my pointer will point to this node. And now systematically what I'll do is I will enter into this loop. So this loop is pointer not null. So yes, pointer not null. So I'll be processing this node. So D gets processed. So I have processed C, B, and now I have processed this D. Now what I'll do is I'll check now whether there is any right child for this D. If there is any right child for this D, once again what I need to do is I need to carry out that entire process for this subtree. Okay, otherwise what I'll do is, so right now we do not have any right child for this D, so I'm going to process this statement. So what is the statement? Set pointer to pop stack. So I'll be popping the element from top of the stack. So this is the element that I'm having on top of the stack. So I'll be popping this 400, and now my pointer will point to this root node. Okay, so I have reached to the end of the loop. So I'm having this end of the loop. So pointer is not null. So I'll be processing this. So A gets processed here. After processing this, what I'll do? I'll check whether there exists any right child. Yes. So what I'll do? I'll set my pointer to the right child. Okay, and now the entire thing needs to be repeated for this right child, because I have done with the left child and I have arrived at this, I have processed this, and I have come to the right child of my root node. So whenever I am having this as the pointer now pointing to this node, I need to do everything, okay, being this as the separate subtree. So I need to go to this R step, and I need to follow once again the entire steps to process this right subtree in the same way, in order fashion. Correct? So what will happen here? Pointer is pointing to this, so pointer is not null. So I'll be pushing this 600 onto the stack, no doubt. And what I'll do is I'll set my pointer to the left of this. So left of this is null. So it will become null. So it will come out from the loop, and once again I'll be popping this. So 600 gets popped, and what I'll do is, as 600 is not null, I'll be processing this. So I'll process E. After processing this E, I'll check whether there exists any right child. Yes, there exists the right child. So my pointer will point to this right child now. That is F. Okay, and I may have the entire tree over here, and that is why I'll jump to R step and I'll repeat this process. So pointer is not null right now. Yes, it is not null. So I'll be pushing that address onto the stack. So I'll push 700 onto the stack. Pointer is set to pointer L child. So pointer will become null. It will come out from the loop. So once again I'll be popping this element 700. It will be stored as pointer. So currently my pointer will point to this 700. As my pointer is not null, I'll be entering into this loop and I'll be processing my pointer. So I'll be processing this F. So I'm processing this F. After processing this F, I'll check whether there exists any right child. If there is no right child, I'll come to this statement. Whenever I come to this statement, I'll be popping one element from this stack. So just look at our stack. We do not have anything in our stack, right? Our stack is empty right now. So whenever I execute this statement, please remember I am having null value associated with pointer. So pointer becomes null, and as pointer becomes null, I am coming out from this loop. And as I am coming out of this loop, I have done with my processing. So everything is done and I have processed my tree in order fashion, okay, using a non-recursive algorithm. So see here how we have developed the logic and how we have made use of this stack. So please remember, whenever we are talking about in-order traversal, right, in-order traversal, then we need to process the left subtree first. So to reach to the leaf node towards left side, whatever comes in, we need to go on pushing every address onto the stack. So we pushed 100, 200, 300. Right? And whenever we come to the leaf node, right, so there is a left child is null now, then the first node that is being processed. Okay, so after processing this, we have stored this value onto the stack. So we may pop that value, we may check whether there exists any right child. If there is a right child, then there is a possibility that the entire structure of a tree is there. So we are going to process in the same way. So this is how our in-order traversal algorithm will work. Please have a look. If you have any doubts, please let me know. Any doubts? So you really needs to think on the logic. So on your own, I would suggest you on your own, take one tree, have such kinds of addresses for every node and try to go through all the steps of this algorithm one after another and try to understand what actually is happening, what is the logic. Correct? So this is regarding non-recursive algorithm for in-order traversal. I'm giving you the exercise now. You should come up with the algorithm for post-order traversal, non-recursive algorithm for post-order traversal. And for post-order traversal, what is the sequence? For post-order traversal, what is the sequence? We first process the left subtree, then we process the right subtree, and then we go for processing of the root node. So left subtree, then right subtree, and then the root node. So try to come up with the logic for non-recursive algorithm for post-order traversal. It is really very interesting to build the logic. Okay? Any doubt? Any doubt? Please speak up. Is there any doubt?
No, ma'am.
Have you understood? Have you understood the concept and the logic for pre-order and in-order? Yes or no? Not understood? So how to interpret this silence? Whether you have understood the concept or not. So if you really would like to excel in building the logics, try to build the logics for such kinds of algorithms. It will help you improve your logic, your logical thinking, and it will help you to build the algorithms for some complex problems. So please try to exercise such kinds of things. And that is why I'm giving you this exercise to come up with a non-recursive algorithm for post-order traversal. We have seen pre-order and in-order. And I'm asking you to come up with the algorithm for post-order traversal. Right, so I'm not going to give you right now the algorithm, but I'm asking you to come up with this algorithm. Now, with this, I would like to conclude our discussion related to algorithm. Only few things those I would like to emphasize is there is one more algorithm, breadth-first pre-traversal algorithm. So in breadth-first, what we do is we go on traversing the nodes level by level. Right? So processing order is in breadth-first is like A, B, E, C, D, F in this particular example. Okay, and simply I am going to give you the hint. If I would like to write the algorithm for breadth-first tree traversal, I need to make use of a queue. And why I need to make use of a queue? Because after processing the root node, right, I am going to enqueue this node towards left, right, then I'm going to enqueue the node towards this right and so on, right. Why queue? Because in the same order I need to process the nodes. So whatever is the order in which I'm enqueuing the node, in the same order I need to dequeue the nodes and process those nodes, and that is why we are making use of a queue. So we are having here the algorithm for breadth-first traversal. I am not going into the details, but you should go through the algorithm for breadth-first traversal also. And this is being implemented using a queue. Okay. Further, after discussion of all those traversal algorithms, I would like to tell you, I don't know whether you know this, the expression trees can be implemented by making use of the binary trees. And this is one of the interesting applications of binary trees, expression trees. And there are certain rules how we can build the expression tree. Do you know how to deal with expression trees? Whether it was included in your syllabus? Have you gone through these concepts?
No.
Yes or no? Have you gone through the expression trees?
No.
Yes sir. No? Or whether you have gone through such kinds of trees? So while building the expression trees, whichever are the operands, this is my expression tree, this is my expression A into B plus C plus D. So whatever are the operands in the expression, those operands are the leaves of my binary tree. And whatever are the operators, those will become the internal nodes. Have you studied such kinds of expression trees before? Yes or no? I want answer whether you have studied expression trees before.
No, but in syllabus it is as an application it mentioned.
But you have not gone through?
No.
Okay. So see here, if we are given the expression, mathematical expression like this, it is possible to represent this expression by making use of a binary tree. And as I mentioned, the rule is the operands are the leaves and the operators will become the internal nodes. Correct? And most important or interesting thing is, if I am having such kind of expression tree and if I traverse this tree in order, pre-order or post-order fashion, then what I'll be getting is the respective postfix, infix and prefix expressions. You might be knowing what is prefix expression, what is postfix expression, and what is infix expression. Barabar na?
Yes.
So if I am having the expression tree, I am not going into the details, only the essence I am explaining you. So if I am having the expression tree and if I traverse this tree in order fashion, what I will get is the infix expression. If I traverse expression tree in post-order traversal way, then whatever I am getting is the postfix expression. And if I traverse my expression tree in pre-order traversal fashion, then whatever I am getting is my prefix expression. So it is really very interesting to study. So if you have not studied, please go through. Right? So simply the expressions need to be represented as an expression tree, and simply by making use of different traversal, it is possible to get the respective kind of expression. So it is really very interesting. I would suggest you to go through. Few exercises for you. So this is one kind of exercise. I do not know whether you have gone through such kinds of exercises earlier. But if you are provided with in-order traversal and pre-order traversal of a tree, say for example, then it is possible to draw the related binary tree. So I'm having lots of such exercises here, and I want you to come up with the solutions for all those exercises. These are really very interesting. You may have similar kinds of questions in your technical rounds to judge your knowledge about trees or data structures. And that is why I have given here few such kinds of exercises. So simply I'll give you the hint. So if I'm having provided with the in-order traversal sequence and say pre-order traversal sequence, and if I ask you to build or draw a binary tree out of this, how I am going to do that? We know what we mean by in-order traversal and we know what we mean by pre-order traversal. In in-order traversal, the sequence is left, then root, and then right. And in pre-order, the sequence is root, then left subtree, and then right subtree. Am I correct? So the simple logic we need to apply. So if I look at this pre-order traversal sequence, then what is the first node that is in traverse? It is F. So definitely this would be the root node of my tree. So while drawing the tree, I may pick this F as my root node. Because in pre-order traversal, the node that is being traversed first is the root node. Right? So simply this will become my root node. Now what I need to do is, I need to look into the in-order traversal and I need to find out the position of that F in my in-order traversal sequence. So I can identify that my F is located somewhere here. So how to interpret now this in-order traversal sequence? Please see here, whatever is towards left in my in-order sequence. So all those nodes will belong to my left subtree of F, and whatever is towards right, that will belong to my right subtree of my F. Is that okay? Yes or no? Got it?
Yes.
Now,
Yes.
after identifying whichever are the nodes in my left subtree and whichever are the nodes in my right subtree, what next I should do? I should refer to once again the pre-order sequence. So after F in my pre-order sequence, I have traversed A. So obviously in pre-order, what is the sequence? Root, then left. Correct? No? So in the left subtree, the node that gets traversed first is once again the root of that left subtree. So whatever node I'll have here is A. Am I correct? So once I have identified this node, I need to check my in-order sequence. Where is the location for this A? So I have found that A is located here. So once again, what I need to understand is, whatever is towards left, that will form the left subtree of this. Okay? And whatever is towards right, that will form the right subtree of this A. Am I correct? So obviously, I will have E in my left subtree, and after A in pre-order traversal, E is been traversed. So definitely this E will go here. And now two nodes towards right of A is C and K. Right? So C and K will form the right subtree of this A. But now what is the exact position of C and K? So what I need to do next is, I need to look for this C and K in my pre-order traversal. So in pre-order traversal, K is being traversed first after E. What does this indicate? F traverse, then A traverse, then E traverse, and then after this, K is traversed. So this indicates that I am having here the node K that has been traversed. Right? So I'll be having K here, and if I look at the in-order traversal sequence, towards left I'm having C. So this means that C belongs to left subtree of K. So I'll be having C over here. So this is how we need to interpret the sequences, and we should come up with the tree. This is really very interesting, and we need to apply whatever we have learned. We need to apply logic, and it is possible for us to come up with such kind of a tree. Okay, so I'm having several such exercises here for your practice. So I would advise you to go through all these different kinds of exercises and build your knowledge. If you have any kinds of doubts, please let me know. So lots of such exercises are being provided with respect to the expression tree as well as the various traversal sequences. I would suggest you to go through all those exercises. Even I have few problem statements asking you to write the algorithms for certain tasks. So I would suggest you to build the logic for all those different kinds of algorithms. And if you have any doubt, please let me know. Right? So this is the session that was intended actually to build your knowledge related to various traversal algorithms and its applications. Right? So I think let us stop today. If you have any doubts, you may come up with the doubts. So is there any doubt right now? Yes? Otherwise, we are going to conclude this session. Yes? Any doubt? Fine. So I hope that you have understood whatever we discussed today. So let us conclude this session. And I would insist you to go through all the exercises. Thank you.